So I want to evaluate the integral from minus infinity to positive infinity of x squared over x squared plus 1 times x squared plus 4 dx. So as usual, using the residue theorem, I will first find the poles. So I will set the denominator here equal to 0. So we'll get x squared plus 1 times x squared plus 4 is equal to 0. So x is plus or minus I or plus or minus 2i, okay? And here I have a pole of order 1, so n is equal to 1, okay, because we have nothing squared in the denominator, okay, we have nothing like something squared to the third power or whatever. You only have to the first power, basically, okay? The whole denominator is not squared or to the third power or whatever, okay? It's only to the first power, so we don't write it, okay? You could write the 1 here, but it wouldn't change anything, okay? Yes. So we can use the residue formula for poles of order 1. That is simply everything above the bar fraction remains the same, and in the denominator, so everything below the bar fractions, we just take the derivative of it. So we take the derivative of the denominator, so x squared plus 1 times x squared plus 4. So we can rewrite that as polynomials simply. So we get x to the 4th plus 5x squared plus 4. Okay, so we just multiply out x squared times x squared times 4, 1 times x squared, 1 times 4, okay? That's all we do. So now we can take the derivative of that, so we get 4 times x to the 3rd power plus 10x as our derivative. Okay, 4 is a constant, so it's 0, the derivative. So now, yeah, we find our residue, or general residue, okay? We can factor out the x everywhere and cancel it, so at the end you are left with x over 4x squared plus 10, okay? Yeah, and now we could plug in the poles, so plus or minus I or plus or minus 2i to calculate the residues. Yes, but first we need to make a choice. Which contour do we take? In the lower half plane along the lower half circle, or in the upper half plane along the upper half circle, okay? As usual, it's usually the same thing. It's just that at the end, if you go in the lower half plane, you go clockwise, okay? Because you start at minus infinity, you go like that, and then you go like this. So this is this is clockwise, sorry. So at the end, you will need to multiply your residues with minus 2 pi I, okay, and not 2 pi I, okay? Because in math, clockwise is negative, and counterclockwise is positive, okay? Or if we go a set in the upper half plane, we go from negative infinity here, like that, and we go up and back to negative infinity. So we would have counterclockwise direction, so we just multiply by 2 pi, okay? And that said, as usual, the residues change. Here, if you are in the lower half plane, you will have negative I and negative 2i in our domain, okay? And if we are in the upper half plane, we would have positive I and positive 2i in our domain, okay? So the residues will change accordingly. So let's choose the part in the upper half plane, so the contour along the upper half circle. So if we have our formula here for the residues, and you plug in x is equal to I, so positive I, we get I over 6, okay? So I squared here, so minus 1, so minus 4, plus 10, so 6. If you plug in x is equal to 2i, we get 2i over minus 16 plus 10, so minus I over 3, okay? So 2i over minus 6, so I over minus 3, so minus I over 3, okay? So now we use again the residue theorem, which states that our contour integral is equal to 2 pi I times the sum of the residues. Again, here our contour integral is made of two parts. The part along the real axis is our part 1, then the part along the upper half circle, okay, in the upper half plane is our part number 2. That is our circular axis. And instead we go counterclockwise. Okay, we start negative infinity, we go like that. Okay. So the part along the real axis, okay, so that is my real axis. Here, this is my imaginary axis. The part along my real axis is simply my original integral. Okay, so my original integral I, big I, capital I. Yes, because we go from minus infinity to positive infinity, and we have just our variable. I mean, we can set x equal to some t, and so we have dx is equal to dt, and the set t is between minus and positive infinity. We can replace every x with t, and we would get the same integral as in the origin. Okay, as here. Okay, it's just another variable, but that variable is a dummy variable, so we don't care. Okay. So our first part along the real axis is our original integral, and now we want to prove that the second part here along this circular axis vanishes as r gets toward infinity, as usual. Okay, so as usual, we will let x be equal to r e to the pi I t. Okay, r is the radius of this circle that will tend toward infinity, and e to the pi I t can represent a circle, okay, like that or like that, okay. And so if t is between 0 and 1, this will represent half a circle in the upper half plane, okay. If t is between 0 and -1, you would have something in the other way around, okay, in the lower half plane. But here we are in the upper half plane, so yeah, we do t is between 0 and 1, okay. Because if we plug in like 0, we get 1 here, so we get just r, so yeah, so here. But if you plug in 1, you get e to the pi I, so -1, so negative r. So yeah, in here. Okay. Yes, and so if you plug in, I don't know, t is equal to 1 over 2, we get e to the pi I over 2, so I, and so we would be here. Okay, so we are rotating, and as I said, if it would be negative, we would have this path. Okay, t is equal to -1 over 2, it would be e to the negative pi I over 2, so negative I, so here, okay, so you would rotate like that, but at the end we would also come to this region here, so yeah, negative r, okay. Yes, so our dx is equal to pi I times r times e to the pi I t dt, and so again we plug in everything with t, and yeah, yes, we have the integral from 0 to 1, because t is between 0 and 1. We have our dx here, so pi I r e to the pi I t dt. We have x squared, so which is now r squared e to the 2 pi I t. We have x squared in the denominator plus 1, so r squared e to the 2 pi I t. And here we have also x squared, so r squared e to the 2 pi I t plus 4, okay. And so that is roughly equal to r to the third power over r to the fourth power, okay, because we have a r squared here plus an r here from the dx. Here we have r squared and r squared, so that is like r to the fourth power, and so that is equal to 1 over r, okay, and so that will tend toward 0, go toward 0 if r gets larger and larger, okay, if r tends towards infinity, okay. So again, this second part here will vanish, and so then we can use the residue theorem. We know that this second part goes away. We know that this first part is our original integral, okay? So we have our original integral plus 0 is equal to 2 pi I times the sum of the residues, okay? So again, as usual, here we have 2 pi I. It's positive because we are going counterclockwise, okay? We are here, we're going like that, okay? We go like this, okay? You can start negative infinity, we go like that. If you had chosen the other way around, you would need to multiply with negative 2 pi I instead of positive 2 pi I, because yeah, we would walk in a clockwise direction, okay. Yes, so now we multiply our residues by 2 pi I, so the residues inside our domain. We said that in the upper half plane you only have x is equal to I and x is equal to 2I as poles inside, so residues are I over 6 and negative I over 3, so those are here, I over 6 minus I over 3, okay, so minus I over 6 plus minus I over 3. Okay, so plus negative I over 3, so negative. That's why there's a negative here, because it is plus negative. Okay, so we get 2 pi I times minus I over 6. Okay, if we can multiply by 2 at the top and bottom. So you would have that. That would be negative I over 6. Okay, and so now times 2 pi I, we get pi over 3. Okay, and that is our final result. Okay, so as usual, same thing. Find the poles, so set the denominator equal to 0. Here we have a pole of order 1, that's lucky, so we just take the derivative in the denominator, and above the fraction bar everything is the same. And then we choose our counter. Here we can choose it, as I said, we don't have something like e to the ix or e to the minus I omega x. We don't have that, so we are free to choose our path, because we don't need to get an exponential decay, okay? Because our fear is that if we get something like e to the positive infinity, it would diverge the second part. This second part here along the circular axis would diverge, and so we could not proceed, and that's not what we want, okay? But here we are free to choose, because I said we don't have e to the ix or e to the negative I omega x, okay? And so it's okay. Then as usual, you calculate your residues inside your domain. So here we're in the upper half plane, so we had poles at x is equal to I and 2i, so we calculate those residues. We use the residue theorem, so that the contour integral, which is made of 2 pieces, 1 and 2, 1 along the real axis and 2 along this circular path, is equal to 2 pi I times the sum of the residues. We prove that the second part vanishes as our radius gets larger and larger, so here, and so now we're only left with our original integral, which is our part number 1 along the real axis, okay? Yes, so 1 and 2, and plus 0, that is our second part, okay, that vanishes, as said, is equal to 2 pi I times the sum of the residues, okay, 2 pi I times the sum of the residues, and we solve and we get our final result, okay? I hope it was clear, and that I forgot nothing, and that you could read it, okay? Thank you.